Hello, Brian Miller-Hicks here, continuing a series of PowerPoints on earth science and geology, focusing on meteorology and specifically on air pressure and wind. Air pressure is the concept that derived from the fact that air has weight, meaning the column of air above our heads is pressing down on us at sea level at a force of 14.7 pounds per square inch, or in terms of other units of measurement, about 29.92 inches of mercury, or 1,013 millibars of mercury. These are all measurements of air pressure. They're very, very useful to understand weather, the movement of air, meaning wind, and other weather and climate related phenomena. So, atmospheric air pressure, as I've already stated, air pressure is the weight of air pressing down on us from that column of air above us in the atmosphere that goes up 30 miles or so. Let's look at this graphic, which shows the basic structure of the atmosphere in terms of the troposphere, which is about 7 miles, from 0 to 7 miles, and then the stratosphere above that, 7 miles on up to, that is, the top of the stratosphere is a distance of about 30 miles above the Earth's surface. Okay, let's look at this red line here. This indicates the changes or variations in pressure as we rise from the surface of the Earth. At the surface of the Earth, as I said, we're at 1,013 millibars of mercury. Were we to climb Mount Everest, as you see behind me, this is Mount Everest, the air pressure is drastically less at a distance of about 5 miles or so, close to 6 miles. The air pressure is only around 314 millibars. This is air pressure that is difficult for human climbers to cope with. Pressure is just too low. We're not getting enough air into our lungs. Then as we go up and up and up in elevation to about 20 to 23 miles above the Earth's surface, air pressure is practically speaking zero. There's so little air, so few air molecules that there's hardly any air pressure. Let's look at this graphic here. This depicts a brave feat by a brave man back in 1961. Captain Kinninger took a weather balloon up into the atmosphere, and at an altitude of 31 kilometers or 19.4 miles, he jumped out of the balloon, free fall, with a parachute, of course, for his landing. But then some 51 years later, Felix Baumgartner jumped out at 24 miles. He also took a balloon in a pressurized cabin and jumped from that. Then 2 years later, Alan Eustace jumped from 25 miles. Mr. Eustace wasn't in a cabin. He just let himself get dragged up, just wearing a spacesuit and a helmet, up to an altitude of 25 miles and then jumped out. Pretty gutsy things to do. All three men survived. As of today, 7 years later, this record still stands. So how do we measure air pressure? Well, Mr. Torricelli, Italian scientist, lived in the 17th century, invented an instrument that he called a barometer that measured air pressure. What he used in his barometers, which looks like a thermometer as you see here, was mercury. His first barometers were quite primitive, consisting of an open reservoir of mercury. Air would press down on the mercury, and the mercury in the tube would rise. If air pressure rose, it would sink. if air pressure decreased. These instruments were actually tested by people hiking up mountains and observing and noting measurements of air pressure relative to levels of mercury. Okay. Now, we don't use mercury in barometers today. First of all, mercury is a toxic substance and is very heavy, so it's really impractical to use a mercury-filled barometer. What we use today is called an aneroid barometer, which is a vacuum box, and rising air pressure causes the arrows on the dial to move up, and as air pressure falls, the arrows on the dial move downwards to this side. So falling and low air pressure means stormy conditions. Rising air pressure measurements means fair weather, very dry conditions. Here's a barograph, which not only measures air pressure, but also records it by means of a rotating circular drum of paper. As air pressure rises and falls, the pen will scribe that as a rising and falling line on the graph. Okay, now that we know a little bit about air pressure, let's talk about wind. What is wind? Wind is simply the movement of air, or a mass of air, from one place to another caused by variations in air pressure. Wind always blows from a region of high pressure to a region of low pressure. Okay, simply the movement of air from high pressure to low pressure. This global map shows a lot of information. I'm not going to ask you to examine it in real detail, but let's look at these little circles up here, these circular patterns. This is an atmospheric pressure map that records or shows air pressure in contours. Means that each contour shows a value for air pressure either higher or lower than the next contour. If you look at these circular areas with the blue H's in the center, these are high pressure areas, high pressure zones. That means that the air pressure increases as you get towards the center, towards the H, and decreases as you go away from it. That means that winds in a high pressure zone blow from the interior, from the center, outwards, because they blow from high pressure to low pressure. A high pressure zone means that air is sinking and actually filling down towards the Earth's surface. As air moves away from the high pressure zone at the Earth's surface, it's replaced aloft or at higher altitudes by air rushing in. The air rushing in higher up is convergence. So the air rushes down into the high pressure zone, sort of piling air up into a column of air, and that results in high air pressure. So sinking air above an area denotes high air pressure because the air is piling up, so to speak, into a central zone of high air pressure. The opposite is true in a low pressure zone. In a low pressure zone, the air is escaping upwards, so it's vacating the area. Low pressure zone means that air is rushing in because air goes from high pressure to low pressure. So the air is rushing into this low and then going upwards and then vacating the low pressure zone at altitude. So the air is getting out of there, it's rising up and away and causing a low pressure zone down below. So because air is rising, it is also bringing moisture with it. And if you look at the equator, let me see if I can see. It's not really good. Oh, here's an equatorial low. So that means that warm, moist air is rising at the equator, along the equator, causing condensation adiabatically, the formation of clouds, and storms. So low pressure zone is typically a stormy zone, whereas high pressure zones, like you see along here, are mid-latitude where air is sinking, compressing, causing drier conditions. So global wind patterns, because the Earth rotates, are set up into cells that are called Hadley cells and Farrell cells. So again, heat and the unequal distribution of heat drives air movement. The unequal distribution of heat means some areas are warmer, some areas are colder, some areas have high pressure, some areas are low pressure. We look at the equatorial low that I just mentioned. Here's equatorial low pressure because air is rising here, rising warm equatorial air. It rises because of heat. The heat causes air to become less dense. It carries a lot of that good tropical equatorial moisture with it as it rises. That warm, moist air condenses into clouds that then rain, so that you have a pretty consistent band of low pressure, moist, low pressure, stormy conditions all around the equator. So equatorial low pressure. So here by the red arrow, this is warm, rising air, and then it'll travel northwards or into higher latitudes. As it cools, it sinks. So this is the sinking air, but by the time it sinks, it's been robbed of its moisture. So this is a high pressure zone with dry air conditions. Okay, so rising air, warm and moist, descending air, cool and dry, rising air, warm and moist, descending air, cool and dry. So if you just look at the northern hemisphere, here's the rising warm air, sinking cooler air. It keeps traveling towards the pole where it becomes a bit warmer up here and rises. So this is a stormy weather area. And then surprisingly, as it goes towards the North Pole, it gets very cold and sinks, and the polar area, the North Pole area itself, is actually a high pressure zone with very cold, very stable air. Let me endeavor to explain the Coriolis effect. The Coriolis effect can be a bit tricky, but it has to do with the rotation of the Earth. Now, if the Earth were not rotating, we wouldn't have all these complex winds and rotating currents of air and spinning lows and spinning highs and so forth. But because the Earth does rotate around its axis, it sets up what we call the Coriolis effect. If you have a non-rotating Earth, and if you fire a missile from the North Pole towards the equator, it's going to go straight from the North Pole down to your target on the equator. It's not going to miss. But since we do have a rotating Earth, and it rotates in this sense towards the east, okay, it is a missile fired from the North Pole towards the equator will miss its target because the Earth is spinning this way. The missile is going to land a little bit to the right of the target, or west of the target, if you will. This is it looking from the North Pole downwards. So again, this is the intended target, and because of the Earth's rotation, it lands off target to the right or to the west. The Earth is rotating in this direction, counterclockwise, as you're looking down onto the North Pole. So, in the Northern Hemisphere, winds, water currents, fast-moving missiles, airplanes, rockets, if they're moving from north to south, they're going to deflect to the right. If they're moving north to south, if they're moving north to south, they'll deflect to the right. If they're moving south to north, they will also deflect to the right. So the net effect of Coriolis is deflection to the right in the northern hemisphere, and the opposite is true in the southern hemisphere. There's a deflection to the left. So a northward moving object in the South Pole, southern hemisphere, would move to the left or to the west. So let's look at how that affects winds and the movement of air. You have an upper level wind. It's got no friction, but it's got a Coriolis effect. Now, the higher the speed of the wind, the more the Coriolis effect is going to take hold. So again, wind blows from high to low. The Coriolis effect wants to drag it back. This is called the pressure gradient force, meaning this is a high pressure contour. This is a low pressure contour. So the wind wants to move from the high to the low, but it's being dragged to the right by the Coriolis effect. And in the upper zone, there's no friction, so it's going to be dominated by the Coriolis effect. And if it's real high speed wind, like a 200-mile-an-hour jet stream, it's going to end up parallel to the pressure contour, actually slip right along that contour at high speed. At the surface, there's two forces in effect. The Coriolis effect, causing it to pull to the right, and the friction effect, causing it to slow and to pull backwards. So the wind is deflected to the right under the influence of the Coriolis as well as friction. So the wind never quite becomes parallel to the pressure gradient contour, but it does get deflected. Another illustration. Here we have a starting point for a wind. The pressure gradient force, meaning that it's blowing from high to low. The Coriolis effect starts to turn it rightwards, and then because there's no friction, it turns completely to the right and slips along in this direction. These are contours of air pressure. 912 high pressure, 900 lower pressure. Now let's look at what happens to winds as we map them on a weather map. Okay, this is a weather map. So these are representations of wind speed. This little target symbol means winds are calm. Let's see, you can find one here in southeast Arizona, and up here in the San Francisco Bay Area. That means the weather of that day includes very little wind. Now let's look at these contours. Here's a 1024 millibars, a 1016, a 1000. So right away you see contours are decreasing in this direction and going from high to low pressure. This is a low pressure zone. Now, because the contour millibar lines are close together, it means it's a steep gradient. It means pressure is decreasing more rapidly across here than it is decreasing, say, from here to here. The more narrow the spacing, the faster the pressure is decreasing or increasing, and the faster that the wind blows. The greater the differential between pressure over a shorter distance, the faster the wind blows. So winds reach a maximum speed as you approach the center of this low. So this symbol here, with a little flag, the winds are blowing at about 55 to 60 miles an hour. That's pretty high wind speed. Up here, they're even faster. They're 61 to 66 miles an hour. Okay. This symbol up here would mean winds are at about 32 to 37 miles per hour. So again, winds are blowing into low pressure. This little circle that you see at the end of this symbol is the direction in which the wind is blowing. The wind is blowing from here to here. Wind is blowing from here to here. Okay. Now that's a low pressure zone. So what do we see in the high pressure zone? Winds are blowing into low pressure, and they're blowing out of high pressure. So this wind is blowing away, away, and away from high pressure, and they're not very fast. This wind is only 9 to 14 miles an hour. So let's take a look at the Coriolis effect on these winds. So because the wind is blowing into the low pressure, if you had a wind blowing from here to here, it would be deflected to the right. Okay, from here to here, it's deflected to the right. If you had it blowing from here to here, it's deflected to the right. That has the effect of putting a spin on this whole system so that it's spinning counterclockwise. In the northern hemisphere, because of the Coriolis effect, winds blowing into a low pressure cell go counterclockwise. That's why hurricanes and tornadoes in the northern hemisphere spin around in a counterclockwise direction. Okay, that's illustrated here. This cyclone zone is a low pressure zone, so winds blowing into it are deflected to the right, setting up a counterclockwise spiral. And the opposite is true with a high pressure zone. It's considered or called an anticyclonic, and winds are blowing in a clockwise spin fashion.